So this week I'm very pleased to introduce our own Philip Stamp, who's professor in our department. So Philip is an expert in condensed matter theory and other parts of physics, but in the last several years he's got more and more interested in gravity and quantum coherence effects and the relationship between these things. And there's some new ideas where there's a possibility of detecting what's essentially quantum gravity in laboratory experiments. And he's going to tell us all about that today. So Philip, it's all yours.
Thanks, Douglas. Okay, so I'm starting here just with doing the usual thing of acknowledging people who've funded me, and likewise there. So let me start off by, I guess, setting the scene here by remarking that for the last century, we've depended on two theories, which are unlike any other intellectual accomplishment in human history. These are quantum mechanics and general relativity. And what's extraordinary about them is that despite our best efforts, we have not been able to make them fail. And they have completely transformed our understanding of the universe over an enormous range. So I've put it here. Essentially, we've probed now scales down to 10 to the minus 19 meters. That's extraordinarily small. It's 4 times smaller in scale than the atomic nucleus. And we've also pushed our understanding of physics up to essentially the size of the visible universe. Now, this is a very large range. The number 10 to the 42, it's easy to write it down, but it doesn't really mean very much because it's just so vast. And I'm not even going to try and give you an idea of how big it is because it's almost impossible. In any case, we have these two theories. Quantum mechanics, as I note here, is used to look at very small things. I show here the way in which the electron distributes itself, the probability cloud for a hydrogen atom in one of its states. And, essentially quantum mechanics, as Dirac remarked shortly after its discovery, made chemistry a sub-branch of physics, but it also, we developed nuclear physics and so on and so on. Essentially everything that happens at the small scale, we are able to understand now using quantum mechanics, which is kind of incredible. At the large scale, Einstein formulated a theory which also works incredibly well, and despite enormous attempts to make it fail, also has passed all the tests. And here are some of the phenomena that have been looked at recently with it. This image here shows, it's actually roughly 5 million light years across. It shows a galaxy in which there's a supermassive black hole, which is emitting enormously powerful jets of material, millions of light years away from the galaxy, which is the small white thing in the middle. Very recently, we've had observations of gravitational waves from mergers of black holes. This is a very exciting new field because it involves an entirely different window on the universe from the electromagnetic window that we've been using for the last 4 centuries. Okay, so these are our two theories, but the problem is they seem to be incompatible. And it's often said, particularly in the popular media, that solving this problem is the holy grail of physics. It's certainly the most important problem in physics. So that's where this is, if you like, our starting point. I call it the great conundrum. How do we resolve this incompatibility? Well, I'm going to start off by just giving you sort of an explanation of quantum mechanics. I'm assuming that there are all sorts of people watching this talk, so I've put technical material into the talk for those who are interested in it, but those who are not interested in it can just listen to what I say and the pictures, which are just as important as the technical material. So let me start off by saying one of the remarkable things that quantum mechanics says about how the world works. It says the following: imagine that we have some particle which starts over here at point 1, and it's going to travel to point 2. And throughout human history, we've always assumed that it just travels along one path. And this idea was formulated much more precisely by Newton back in 1687 in the form of Newton's classical mechanics. Quantum mechanics says, no, that is not how the world works. In fact, it says the particle can actually follow simultaneously all possible paths between 1 and 2, and it will do so. This way of formulating quantum mechanics was actually first written down by Feynman. In fact, it was part of his PhD thesis, which was not, the work wasn't published for a long time afterwards because of the war. So you see here, this shows two possible paths for a particle going between 1 and 2. And while it does this, the particle could be emitting, say, photons and then reabsorbing them, or actually it's supposed to be gravitons. But in any case, this quantum mechanics says it follows all possible paths, and we have to sum over all of them in order to find out what is the probability for it to go from 1 to 2. For those of you who are interested in the formalism, this is how we write down that statement that I just made. Now, the point is that not all paths are weighted equally. And this is another very old idea, which goes back to the Dutch astronomer and mathematician Christian Huygens, who argued that we could explain the motion of light as a wave, and that we should think about the wave as passing through all possible paths between one point and another. So Feynman's idea was really resuscitating a very old idea. However, it's not quite the same, because Feynman attaches a weighting to each path, which we have when we sum over them. The point is that the particle travels along each of these different paths as though it was a wave. The wavelength can be very short or very long. We're all accustomed to very long wavelength radio waves and very short wavelength gamma rays, but this is true for everything. So for example, I'm showing here a fast moving particle, which has short wavelengths, and a slow moving particle, which has a long wavelength. Now, the interesting thing is that these wavelengths for massive objects are very short. So if I have a sand grain here moving at 1 meter per second, roughly walking speed, then that wavelength is 10 to the minus 26 meters, fantastically small. But if I choose a really light object like an electron, moving again at 1 meter per second, that wavelength is 1/10 of a millimeter. So big objects have short wavelengths, and so this is why we don't actually see quantum mechanical behavior for these big objects. Now, this is just the standard view that I'm giving you. This is what you would find in a textbook. In the course of doing physics according to quantum mechanics, we've discovered that there are what we call 4 forces which mediate interactions between particles. Now, these forces, I'm going to give you what most particle physicists would regard as a very dumbed down version of this, but let me just do it because I think a very nice point comes out of this simple analysis. So the Maxwell field, that's the electromagnetic field, is one that everybody's familiar with because light is a manifestation of it. Also radio waves and X-rays and so on. So the key point that was understood very early on is that this was actually Coulomb that discovered this, is that the force between two charges is mediated by this electromagnetic field, and it falls off like the square of the distance between the charges. And in quantum mechanics, we say that there are photons traveling between the charges, which are mediating this. So this is a force between electrical charges. There's another interaction, the weak interaction, which actually behaves rather differently. It doesn't fall off like 1/r². There's also this exponential thing, and is mediated by things called W bosons. Then there's the strong interaction, which actually becomes a constant at long ranges, and it's mediated by gluons. Now, all of these forces can be incorporated into a theory, which is usually called the standard model, and which works unbelievably well. And this is a triumph of particle physics over the last 50 years to have attained this theory and to use it. But there's this other force here, the gravitational force. And this is mediated in quantum theory by gravitons. And it also looks just like the Coulomb force. It falls off like the square of the distance between two masses now. The difference is that G here, this constant in front, is very, very small, which means that the gravitational force is very, very weak. That's one thing that one notices about the gravitational force. The other thing is that it doesn't fit into the scheme, the quantum mechanical scheme, which all of these other forces fit into. Let's see why that is. Well, everybody knows that the energy of an object can be equated to the mass times c squared equals mc squared. In other words, one can convert this mass into energy. But one can also write this as the mass is given by the energy divided by c squared. Now, excuse me, we can rewrite this just by using the discussion here that I gave about the relationship between wavelength and momentum as in this form, we say that the mass is going like Planck's constant divided by the velocity of light divided by the wavelength. So as the wavelength gets shorter and shorter, the mass gets bigger. But that wavelength is basically just like the distance between two masses, which means that if we now substitute this in to the force law here, we find that this force blows up. And it doesn't blow up like 1 over r squared, it blows up like 1 over r to the fourth. Now, it blows up only at very, very short distances. I'm going to explain to you in a minute what this thing here is. It's called the Planck length. And it blows up basically when the distance between the masses becomes of order the Planck length. So we have to go to very short distances to see the blow up. But this blow up, in technical terms, means that gravity is non-renormalizable and it can't be included into the usual scheme. Now let's look at some numbers here. Let me first of all, before I give you the numbers, let me just show you what the picture is that they lead to. So this graph, which is very well known by particle physicists, is sometimes called the Royal Road to quantum gravity. And it's basically a map showing us how far we've gone and how far we have to go before we get to the energy scales that are involved in this blow up that I told you about. Before, in fact, this becomes a real problem. So back in 1900, we were able to use X-rays, and we could say that physics had got to the point where we were able to do experiments at the energies of X-rays. And never mind what a kilo electron volt is, that is, if you like, a measure of the typical energy of the X-rays that people were messing around with at that time. We're now in 2021 AD, and we've gone from 10 kilovolts, kilo electron volts, up to actually 10 to the 4 giga electron volts, which is 10 to the 13 electron volts. So this is actually, we've gone up by a factor of 1 billion in energy in the last 120 years. And what this means in quantum mechanics, because higher energy means shorter wavelength, as I was showing you before, which means we've gone to shorter and shorter distance scales in our probing of, if you like, of the physical world. We've gone to 10 to the minus 19 meters. But look how far we have to go before we start seeing, if you like, quantum gravitational effects, where quantum mechanics and gravity start to lead to interesting features where the effects become big. It's a very long way. So this is where we are now with the LHC, and this is where we have to go. And you see that we're actually having to increase in energy by about 10 to the power 15 and go down in length scale by 10 to the 15. Actually, a little more than that, 10 to 16. If you extrapolate this graph, we'll probably get there about the year 2500. So we've got a long, long time to wait before we can probe this in the kind of experiments that are done by particle physicists. I'm not going to go through these numbers here. It's the sort of thing that you sit down with a calculator and you figure it all out. But basically, there are length scales, mass scales, and energy scales associated with these high energies, and they're very high energies indeed. This energy up here, the realm of quantum gravity, is, I've written it as 10 to the 19 GeV, but just to tell you what that means, it's a Planck energy, that's what it's usually called. If you deposited a Planck energy in 5 tons of water, you could raise it from freezing point to 100 centigrade. That's a huge amount of energy to be talking about for particle physics experiments. In fact, you would require to do particle physics experiments at that energy, you would have to deposit that energy in a length of order the Planck length, which is 10 to the minus 35 meters. This is the only time possibly that there have ever been conditions like this in the universe at the very beginning of the universe. So people are trying to do theory up here in a realm which is not going to be accessible to experiment for perhaps 400 years if we extrapolate in this way. And it's not easy. So this is a statement just a few weeks ago from Hiroshi Oguri, who is a string theorist. He says, it is not well appreciated how hard it is to build a consistent theoretical framework to unify general relativity and quantum mechanics. Well, that's definitely true. He then goes on to say, currently, superstring theory is the only credible theory to have achieved the unification. Doesn't say that it'll take 4 centuries to test it, but he asserts that superstring theory does the job. Well, I'm actually going to argue that that is not true in this seminar. Let me first of all, having described a little bit about quantum mechanics to you, remind people who haven't seen it before what general relativity is about. Basically, it's a way of understanding space-time as not just some passive receptacle for events in the physical world, but as a thing in its own right. And Einstein essentially picked up where people like Euclid and Gauss and Riemann had looked. We asked the following question: so how do we define length, for example, in space? Well, we were taught in school that there's a thing called Pythagoras' theorem, which tells us that the length on this diagonal here is squared is equal to the sum of the squares of these other two sides. And that defines Euclidean geometry. And I've written it here. Now, the idea is that you can have non-Euclidean geometry in which this is no longer true. Here's a really nice example of this. Imagine that we live only in 2 dimensions, so that we're not even aware that there are higher dimensions. And we try and verify whether Euclid is right. So we move around, making, for example, right angles here. And this is another example where we move around making right angles, and we discover that this is not true. And we say, oh, well, even though we can't go outside of the space that we're living in, it must be curved. And mathematicians will write this down in the way that I've shown. But Einstein argued, his theory asserts, if you like, that space-time, which is not 2-dimensional but 4-dimensional, is also curved. And in fact, we can map it not by rulers, but by light beams. And this shows how, for example, you can look at the distance between 2 curves in space-time by bouncing light back and forth. And here, this shows you what happens when space-time is really strongly curved. This is in the vicinity of a black hole. This shows the paths of photons as seen from outside. You see that as we get closer and closer to the black hole, light is actually bent around and eventually orbits the black hole. And if it gets too close, then it just falls in. This is for a spherically symmetric black hole. Most black holes, in fact, pretty much all of them are rotating, and then the path is even more bizarre. And so you can see that, in a sense, light is allowing us to map the curved space-time. Again, this is all technical. For those who want to hear more about it, you can just read this. But the key that Einstein, the key result that Einstein achieved here, it's called his equation of motion. It says that you can relate the curvature of, well, I call it the distortion of space-time, because it's more than just curvature, it's twisting and stretching and so on in space and time. But there's this quantity here, which is called the Einstein tensor, which is essentially telling you how much space-time has been stretched, curved, and twisted, and so on. And Einstein said this is actually equal to something else called the energy momentum tensor, which is actually, if you like, a measure of the local stress in space-time. And it's created by energy and momentum. So imagine that you have a very large source of energy at some point, then that will actually distort space-time. That's exactly what a black hole is doing. It's a very, very high concentration of stress energy, and it distorts space-time. But there's a very interesting thing that comes out of this result. We're saying that space-time distortion is linked to energy. But the thing is that the distortion of space-time carries energy. And this leads to something extraordinary. Space-time distortion will feed on itself. It has energy, but that energy creates more distortion. And so the whole thing can actually blow up. That's essentially what a black hole is. But it means that space-time curvature generates more space-time curvature, and it means that empty space can actually carry energy in the form of, for example, waves. This is gravitational waves. So this is showing you in 2 dimensions how a gravitational wave would distort the space-time. And this has led to, this simple fact here has led to all of the extraordinary consequences of general relativity, from the scale of Earth-bound experiments looking for gravitational worlds to the discussion of the entire universe. So we've got these 2 theories, and they're both pretty amazing. Problem is that, as I said, they disagree with each other. Actually, they both have problems. Quantum mechanics, I won't go through all of this, but it's very peculiar because the way it's formulated is always in terms of measuring system formulas in quantum mechanical. They behave as extraneous, non-quantum agents. I think that many people in their deep secret hearts would agree with me that this sounds rather medieval. We're making the entire apparatus of physics depend on measurements made by humans. And a number of physicists have characterized this rather ruthlessly. For example, Bell remarked that he couldn't understand whether a bacterium could make measurements or not, in which case, if it couldn't, then obviously the universe didn't exist before humans, because everything was supposed to depend on human measurements. Feynman simply remarked that he didn't understand quantum mechanics, and he didn't think anybody else did either. This was in his Character of Physical Law lectures. So it's a peculiar theory. But general relativity is also not immune from problems, because it leads to singularities. And most physicists think that these singularities can't possibly survive a better theory. Even though it is a remarkable theory, they think that it's also got to go down, as it were. Now, I was talking to you about the view of string theorists. They think that superstring theory has actually achieved the unification. But there are, in fact, lots of problems like these, which are ignored in string theory. And in fact, one can argue that there are fundamental problems not at the Planck energy, which is absolutely way beyond any experiments, but actually in the ordinary world of tables and chairs that we live in. So let me tell you about a classic experiment in physics. It sometimes goes under the name of the Cavendish Experiment, but it also goes under the name of the 2-slit experiment. We imagine an object which can follow 2 paths in quantum mechanics. Remember, I told you that in quantum mechanics, an object doesn't follow just one path, it follows lots of paths. Imagine that it can follow 2. The reason I'm showing this as an apple and an orange is because, as I'll explain more, gravity doesn't distinguish between different kinds of matter. All it sees is their stress energy. So if you have an apple and an orange which have the same mass and density, then as far as gravity is concerned, they're the same. But you can do an experiment called the Cavendish Experiment to test which path this object followed. And in quantum mechanics, you have to describe that as a superposition of states. And if you're going to include gravity, you have to include gravity in that superposition of states. But all sorts of people, and I'll say a little bit about the history, have found this extremely objectionable. First of all, they don't know what it means to superpose, to have 2 different space-times. And formally, in fact, it makes no sense at all, because you can't even define quantum field theory under these circumstances, because you don't know whether 2 events are space-like separated or time-like separated if there are 2 different space-times, which means that the whole of quantum field theory more or less collapses. For those of you who are interested in the details, you can read this. But all of these considerations indicate that even in our own everyday world, there's a problem if you like, there's an irreconcilability between quantum mechanics and gravity. And if that's the case, then we don't have to go to the Planck scale, and we don't have to wait 400 years to do experiments. We can actually do experiments now. In other words, we've been looking, like Sauron searching for the hobbits, we've been looking in the wrong place to solve the problem. So let's see what to do. Okay, you know, we've got to figure out a way of, if you like, combining general relativity and gravity, and that's not easy, as was pointed out by Guri. Feynman was the first person to really talk about this problem and argue that maybe quantum mechanics would break down because of gravity. He did this in 1957. And his question then was, how can we possibly proceed, since it's impossible to do experiments of this on this sort of thing? And he argued that, well, we could either try and figure out some mathematically rigorous theory, but he argued that that was just pointless. But he said, what we can do is do thought experiments, just like Einstein, and calculate with them. So let me say a little bit more about what Feynman argued. So this is from his Chapel Hill lectures in 1957. I would like to suggest that it is possible that quantum mechanics fails at large distances and for large objects. So this is exactly the opposite of what we were saying at the beginning of this talk, which is that it only failed at short distances. If this failure of quantum mechanics is connected with gravity, we might speculatively suggest that this would happen for masses, essentially of the Planck mass. So that's 10 to the minus 5 grams, which corresponds to some 10 to the 18 particles. Now, the reason why Feynman argued that it was impossible to do experiments was because nobody knew how to do experiments showing quantum mechanical behavior for something that big at that time. Later people tried to argue in a similar vein. Penrose, for example, proposed various ideas about dephasing being caused by gravity. So it looked as though there was some decoherence caused by gravity, but he was unable to find a theory. In fact, he remarked very clearly, none of the considerations of the present paper, that's the paper here, give any clear indication of the mathematical nature of the theory that would be required to incorporate a plausible gravitation-induced spontaneous state vector reduction. Like many British people, his sentences are quite long. Much more interesting, at least to me, was work by Kibble, who attempted to make a nonlinear quantum mechanics by incorporating gravity into it. And he discovered that this was impossible. If you tried to keep the usual quantum mechanical apparatus, the structure of operators, measurements, and Hilbert space, it wasn't going to work. And similar efforts were made by Steven Weinberg and Joe Polchinski, who really nailed down the problem. So it looks as though, from all of this, that if we're going to find a breakdown of quantum mechanics, as suggested by Feynman, we're going to have to do quantum mechanical experiments for big objects. So you can ask the following question. People often assume that quantum mechanics works for everything, but does it really? People have done experiments here, and essentially what's been found is that nobody has managed to prove quantum mechanical superpositions or entanglement for objects containing more than roughly 10 to the 3 particles. That's a long way from the macroscopic scale. Again, if people are interested, they can look at the details. So what this means is that in spite of the fact that people use, for example, quantum mechanics to describe the universe in cosmology, there's absolutely no evidence whatsoever that it should work at that scale. So what do we do? Well, here are some recent developments that I'm going to describe. I'm going to talk a lot about experimental tests of various ideas, including the Penrose dephasing, later in this talk when I come to experiments. Let me quickly deal with something which has developed a huge literature over the last 40 years, which is the idea that somehow the collapse of the wave function in quantum mechanics could be caused by some external noise field, which is linked to gravity. Now, many physicists feel that this is a ridiculous idea because it doesn't even conserve energy. This noise field is coming from outside the universe. But it does have consequences, even though it's not really predictive, because if such a noise field exists, it would not only cause random heating events, but it would also shake objects and cause them to emit radiation. And in fact, very recently in this paper, it is claimed that this whole idea has been disproved. What's remarkable about this paper is that the authors of it are actually also the originators of the theory. what I'd like to do is tell you now about a theory which actually does start from fundamental principles and is quantitative, which is one that I've developed with collaborators. And the key point here is the following. Remember, I showed you that in quantum mechanics, the objects follow many different paths simultaneously. But these paths are independent. They don't see each other. But there's a very interesting thing that I already mentioned about gravity, is that it doesn't distinguish between different paths. All it sees is the energy momentum associated with them. And in fact, it can't even distinguish multiple paths for a single object from multiple paths for multiple particles. So what this means is that because the gravity doesn't see the difference, it can also interact between these paths. One path will see another via gravity. So what this immediately involves is a breakdown of quantum mechanics. And the question is, can you make a theory out of this? Well, I have actually, people who want to find out more details can look at these references. I understand from Douglas that this talk is going to be online. And I'm not going to go through the details because this is a colloquium, but these details are there for people who want to see them. I'd just like to tell you a number of results. First of all, one finds that the theory is internally consistent. Remember that Oguri, the string theorist, told us that it's almost impossible to find a consistent theory combining general relativity and quantum mechanics. Well, actually, we've shown that this theory is consistent. It's not only does it satisfy all of the consistency tests that one can think of, but it's also renormalizable, which, remember, conventional quantum gravity is not. These results are a big deal because it's very, very hard to find a consistent theory combining quantum mechanics and gravity. I'm not going to go through all of this. I'll just tell you in words one of the key features of the theory. It turns out that general relativity for space-time is preserved. In other words, the space-time field still obeys general relativity. However, matter fields don't. They interact with each other through the paths for a single matter system interact with each other through gravity. So we have a very peculiar situation in which classical space-time field still behaves classically, but it causes interactions between paths for matter fields, which cause a breakdown of quantum mechanics. So what does this theory predict? And again, I'm quoting Feynman here. I've always liked this quote. This is where he was asked by somebody, how do you define a theory? And he said, well, I can tell you what a theory is not. If it doesn't produce a number, it's not a theory. And again, I'm going to avoid this, all of this technical detail. For people who want to look at it, it's there. It's also in the papers. But one can actually write down a perturbation theory for this, and you get what look like Feynman diagrams, but are not. And the reason is that you can start with a single particle, and two paths will interact. So this is not a diagram you could ever see in conventional quantum theory. And in fact, multiple paths can interact. You can see that gravitons here are being exchanged between two paths, between three paths, and so on. It turns out that there are very interesting rules which govern these diagrams. As I say, they're not really Feynman diagrams, but these diagrams are governed by very interesting rules. And in fact, one can show that it's possible to sum them exactly. So that there are these exact results in the theory. But let me explain what the physical content of all of this is. Imagine I start with a particle over here and it tries to propagate to here. But there's this interaction between the paths, which, as I say, is a violation of quantum mechanics. But what that means is that the paths are attracting each other. So this means that instead of the different parts of attract each other, this, of course, is going to lead to a difference with conventional quantum mechanics. And one would like to know how that happens. So this picture here, and again, this is for the people who want to know about the formalism, but here I'm going to show you what happens if I have a slow-moving object. What happens to its dynamics? Well, the point is you have this attractive interaction, which for a slow-moving object is just Newtonian, between different paths for a single particle. And you would think naively that that would simply cause the paths to collapse onto each other. So people, when they first saw this theory, said, you're causing collapse of the wave function. But this is actually not the case. Because in fact, what happens is exactly what would happen if you had two particles interacting with each other through a Newtonian force. They would actually orbit around each other or scatter off each other. So this is what the paths would actually look like. You would see two paths for the same object, essentially doing this oscillatory dance with the interaction shown here with these lines. And so one has to think a little harder about how this theory behaves. So we imagine that we've got a particle which is just, moving along quietly in intergalactic space, so it's not interacting with anything else, but it can't propagate in the same way that quantum mechanics says, because the different paths for the propagation are actually attracting each other. So let's have a look for a single particle at what this attractive potential looks like. This is just the Newtonian 1/r potential. But there are various numbers or parameters associated with it, which mean that actually for small objects, this attraction is completely negligible. Let me show you some numbers. So I have a graph here which shows on the x-axis the mass of an object which is moving through intergalactic space. So you see that down here, I'm at a mass of 10 to the minus 30 grams. That's for an electron. Up here, I'm at 10 to the minus 10 grams, and up here, I would be at, say, 1 kilo, way up here. Here, I have a length scale, which is varying from the Hubble length, that's the radius of the visible universe, way down to length scale here, which is the Planck length. And so we see we cover a lot of different lengths if we go along this graph. Each the distance between each of these is a change of 10 to the 10. Okay. Now, what is this length scale? This length scale is actually just, if you like, the analog of the Bohr radius for this Newtonian potential. It's telling you, roughly speaking, that the scale over which these oscillations will occur. For an electron, we see that the length scale is actually 6 million times the Hubble radius. Now here, I'm going to ask, what is the energy scale? And what is, if you like, the binding energy for these paths? How strong is the attraction between them for a particular mass? Well, again, I'm showing the mass here, and this is the energy scale. Actually, it's just in electron volts. So this is very, very high energy. This is actually the Planck energy, and this is an unbelievably low energy, 10 to the minus 80 electron volts. And we see that when we're looking at an electron, the paths attract each other by a force which is so utterly feeble that we would not expect to see anything. We have to raise the mass an awful lot before we start to see an attraction between these paths, which is going to have any measurable consequences. And in fact, this is telling you that if we have a mass of roughly 10 to the 13 hydrogen atoms, we're going to see something. This is going to have a measurable effect in experiments. It's not as big as the Planck mass, which is what Feynman was arguing. It's about several thousand. It's actually about 5 orders of magnitude smaller. Now, actually, this toy model that I've showed you misses a whole lot out. There's interactions between multiple paths, and of course, there's emission of stuff going on because these things are accelerating. So one can fix this. First of all, you can do things not for a particle, but for an extended mass. And then you find that this potential here no longer looks like 1/r. It's actually got a parabolic well with these spikes here, which I won't go into. But the key point is that the oscillation time scale in the well here is roughly 16 seconds, and it's independent of the mass. That's a really key result. It only depends on the density of the object. So for example, if I take a piece of quartz, a sand grain, and I ask, what is the oscillation rate in this potential well? It's about 16 seconds. And in fact, so what we're saying is that if I take a piece of sand and I ask, what is the oscillation time for paths that are interacting with each other? It's about 16 seconds if this is made of quartz. So you say, well, that means that we should actually see measurable effects for sufficiently large objects. Instead of seeing them propagate according to quantum mechanics, there should be this funny oscillatory dynamics of the path. The problem is that if the two particles are executing this dance with each other, they'll just keep on doing so for all time, and they won't collapse, which is what we really want to see. That's how we'll see the particle behaving classically. And the only way they can do that is by emitting radiation. The problem is that in many experiments, one sets it up so that the coupling to the environment is really, really small. And so the time scale required for these paths to, as I say, bunch, to fall into each other and for us to get back essentially classical physics can be very, very long. I'll tell you just how long in a minute. Don't bother about this. This is just redoing the two-slit experiment in this language. But let's just ask how long it takes for the paths for a given object to collapse onto each other so that we get essentially classical dynamics. In other words, how long does it take for this path bunching here to occur? For all the different quantum mechanical paths for a given object to collapse onto each other so that it looks like it's behaving classically. Well, if we were doing this with a LIGO mirror, operating with its normal Q factor, it would take 5,000 years, which means that in a LIGO experiment, we would not actually see the mirror behave classically for a very long time, unless we were able to reduce the Q, in other words, increase the dissipation. Designing experiments to test this theory. I can't really tell you what they are because they haven't been published yet by them, but they are extremely clever, and will get past this problem to show the path bunching. So that brings me to the topic of experiments. So let's have a look at the different kinds of experiments that different groups are actually using to look for a breakdown of quantum mechanics caused by gravity. And of course, what this means is that for a theorist, you now have to do real calculations for real experiments. So let me tell you about some of these experiments. Here is if you like, a cartoon view of one kind of experiment. You take a moving, it's basically doing exactly what I was talking about before, having a mass propagating in empty space, but putting it into a superposition of two states in different positions. This is often called a mass superposition by the experimentalists. So we basically imagine that the system is not in one place, but has actually been put into a state where it's in two different places at the same time. In other words, it's following two different paths which are displaced from each other. And here are some recent papers which are discussing this experiment, and I'll say a little more about them in a minute. So that's one way to try and test the theory. You look to see if this superposition, this mass superposition, behaves differently from what quantum mechanics predicts. Do you see the oscillations that I've talked about? Do you see a collapse into one, if you like, classical state for a large mass? So that's one kind of experiment one can imagine doing, and I'll tell you more about these experiments in a minute. But another way to do it is actually to look at interference between these different paths here and ask whether the oscillatory behavior will appear. And that kind of experiment is actually, here's an example of how it's done. It's a very clever experiment. So you imagine doing the following. We imagine a photon coming in from the left, a pulse of light. And here's a beam splitter which splits the photon into two beams. In quantum mechanics, the way we're different states, one of them following this path, the other one following that path, but it's still one photon. And then we end up with a situation where the photon can either be in this cavity here, so it's just sitting there, or in this cavity here. Well, it's not either or, it's actually in a superposition of the two states. The difference is that in this cavity, this mirror here is essentially on the spring, and when the photon is in there, it actually pushes it, it moves it back. This is because of light pressure. So we then have a situation where if the photon is in this cavity, then the mirror moves. whereas if it's in this cavity, it doesn't move. And in quantum mechanics, it should be in a superposition of the two. Now, in a theory like the CWL theory, you would see something quite different because these two would interact. In fact, the two different positions of the mirror would interact with each other gravitationally, and you would get different results. So that's another kind of experiment. I should say that experiments like this are being done in lots of places, but I'm going to talk about the ones being done in Vienna. Experiments like this are being done also in lots of places, particularly in Santa Barbara and in Leiden in the Netherlands. I've already told you about the problem of decoherence, so I won't talk about it again. Here are some of the experiments. This is recent progress, if you like. One kind of experiment, which I learned yesterday is of great interest to Roman Krems here at UBC, involves clamped oscillators. These experiments actually turn out to be much harder to make work practically than one hoped for. And so most of the experimental groups have now abandoned these experiments. But the idea is that you put the mirror on this object here, which is essentially like a diving board. It can oscillate, and then this, if you like, will become the platform for the mirror in the experiment that I talked about in the last one. Another kind of experiment involves doing essentially the two-slit experiment. You pass an object between so that it follows it can follow two paths through two different slits, and you look for interference between them. As I mentioned before, the largest experiments for which this has been done in real two slits are actually very small. The molecular weight of these molecules is only about 10 to the 5. But the idea is now that one does this interferometry now using heavy masses of the kind that we saw here or here, rather than passing them through slits, we look at interference between their positions, as I showed here. So we won't actually be doing a two-slit experiment, but we will be doing interferometry. Finally, there's the levitated experiments, and these are the ones that have made the most progress recently. So I'm going to tell you a bit about them, and so we can see how the experiments are proceeding. So this picture here is kind of interesting. I got this from Markus Aspelmayer in Vienna. So he's showing how the experimentalists are proceeding. I should say that experimentalists tend to only listen to theorists when it's interesting for their experiments. Otherwise, they're basically explorers in their own right, and they have their own criteria and motivations for doing what they do. But here is the way at least one experimentalist looks at this field. So there are two ways that one can approach this crucial regime where we expect to see the breakdown of quantum mechanics. You can either approach it from the quantum regime. You can do experiments on small objects. Notice the masses here. This is 10 to the, this is the mass. This mass here is, we're talking large molecules here. Up here, we're talking about much larger objects, which I'll show you in a minute. But the idea is that as time goes on, experimentalists are pushing this boundary to higher and higher masses and showing quantum mechanical behavior for these objects. But there's another group of experimentalists who are only interested in classical gravitational phenomena, things like the gravitational field generated by a small mass. And they're doing more and more sensitive experiments, and they're pushing down. And the idea is that when these two meet, we'll have to decide whether systems are behaving according to classical gravity or according to quantum mechanics. And you can see that they're getting closer and closer to each other. There are various predictions made by experimental groups about when these two will meet. One of them was actually made in 2012, and it predicted that they would meet in 2020, which has actually not happened. But it's clear that it's going to happen pretty soon. Let me show you on the left-hand side here, the largest object that has shown quantum mechanical behavior in the form of interference phenomena for a single mass. This is an object which contains 10 to the 9 atoms. It's essentially a quartz particle. This was done in Vienna, and it was published just not very recently. That's a big object. So the molecular weight is 10 to the 11 hydrogen atoms, roughly. And you can see it here, suspended by essentially a photon field. So that's this part. On the other side, we have experiments being done, purely classical gravitational experiments. This is the smallest object to date. It's actually a millimeter across, which is for which classical gravitational effects have been verified. It was essentially, if you like, an updated version of the Cavendish experiment. Now, these are getting closer and closer together, which means that the expectation is that in a few years, the verdict will come in. Does gravity break? Does our classical understanding of gravity break? Does quantum mechanics win? Or does quantum mechanics break down because of gravity? So this is, if you like, where we are experimentally. And you can see that every year, this green part moves to the left and this brown part moves to the right, and it won't be long. So stay tuned, I guess, is the advice given by the experimentalists, and wait to see what happens. So that's, if you like, the discussion I wanted to give of the experiments. And it's essentially, it's telling you that something exciting should happen soon. So I'd like to just finish by thanking the various people who've been involved in this work with me and who've given me all sorts of useful ideas. So my direct collaborators are Andrei Barvinsky from Moscow, Dan Carney, who's now at Berkeley, Yanbei Chen, a close collaborator of mine at Caltech, and then my two students, Colby Delisle and Jordan Wilson. Jordan, by the way, just got his PhD yesterday. And then there's what we call the G5 group. This is a group of us who are working together, trying to understand all of this. One of them, of course, is here. That's Bill Unruh. And the others, Marcus Aspelmayer in Vienna, Yanbei Chen in Caltech, and Birgitta Worley in Berkeley. And there are various other people who have helped me enormously in long discussions about all of this. And I should point out in particular Joe Polchinski, because he was the one that first told me that I should publish these ideas. Very unfortunately and tragically, Joe died. Joe was a string theorist who had an enormous interest in these foundational questions as well. And if it hadn't been for the discussion I had with him, I probably would have waited a long time before publishing some of this stuff. So that's the end of my talk. Thanks very much. Okay, so let me make two remarks here. The first one that I want to make was already made a long time ago by Tony Leggett. He points out that although it looks as though something like a Bose condensate or superfluid helium-4 or a superconductor actually involves quantum mechanics at the scale of the total number of particles involved, that's actually wrong. In fact, the state of, let's consider a superconductor. You have or a Bose condensate. You have all of these particles in a Bose condensate, which are essentially in the same state. But it was actually explained a very long time ago by Phil Anderson that you could map that to a very similar system, in which each Bose system, each atom, if you like, that was Bose condensed, could be mapped to a spin. The direction of the spin corresponded to the phase of the Bose atom. And there's no, it's very easy to imagine a spin system in which all the spins are pointing in the same direction. It would just be a classical magnet. And there's no macroscopic quantum mechanics involved there. The only thing that's involved is that they're all in the same state. So this was explained back in 1980 by Tony Leggett, who pointed out that the real test of whether or not the system was behaving quantum mechanically was through entanglement. And the entanglement, in fact, in these Bose systems is very, very small. He proposed all sorts of tests to see whether superfluids could behave quantum mechanically, whether you could get entanglement at the larger scale. And those experiments were done, lots of them. And this was the result, that the level of entanglement in these experiments was, well, in this experiment done in SUNY, it was up to maybe 6,000, but most of them it was order of a couple of 100. So in other words, the kind of things that you're talking about were already done some time ago. And the result is that if you like, the level of the term that's used here is macroscopicity. How macroscopic is the quantum behavior is actually very small in these systems. Thank you very much. Very good question. So let me, let's see. Yes, here we are. There's a fundamental difference between a gravitational interaction and any other kind of interaction. This is that gravitation not only sees everything, gravitation is completely colorblind. All it sees is the energy, if you like, the stress energy of an object. It doesn't care whether it's made of fermions or bosons. It doesn't care whether it's one particle or several particles. It simply can't distinguish. That is not true of any other interaction. All other interactions all other interactions do see different things. So the electromagnetic field sees charge, and so on. And in this sense, there's no possible way that you can apply this argument to any of these other interactions. There's no way that you can say that the electromagnetic field is not capable of distinguishing two charges whose sum is, say, 1, from one charge which has a charge of 1. It's quite clear that in ordinary quantum electrodynamics, those two situations are not the same. And so the idea that you would have a breakdown of quantum mechanics with these interactions between the paths for any other interaction makes no sense. You only get this, if you like, indistinguishability working for gravitation. And so you can think of this as a kind of an Einstein argument, a thought experiment. You argue, is there any possible way for gravitation to tell the difference between a pair of particles or a single particle following two different paths? And the answer is no. And if it doesn't distinguish, then we should assume that the theory doesn't distinguish either. And that immediately leads you to these interactions between paths. But you can't make that argument for any other kind of interaction. Very good. It's not exactly the equivalence principle. It's more the idea that minimal coupling extends to the interaction between paths as far as gravitation is concerned. It's like the equivalence principle, but if you like, you're generalizing the equivalence principle now to include even interactions between paths for the same particle. But the way you write down the theory, you have to write, I mean, you probably know that there are different forms of the equivalence principle. People talk about strong equivalence principles and weak equivalence principles and so on. But here, essentially, it's minimal coupling. Right. So, I mean, the easiest way is to set up the same kind of thought experiment here for an electron. Okay. Now, excuse me. So we know that the electromagnetic field, actually, the electromagnetic field sees not only the charge but also the spin of the electron. And if I go to different reference frames, it will see the spins pointing in different directions. So in that sense, the electromagnetic field is perfectly capable of distinguishing between an electron following this path or that path. However, in the case of gravity, the stress energy tensor is, of course, a relativistically invariant quantity. And so there's absolutely no way that the gravitation will distinguish between a single electron here a single electron following each of these paths, or one electron following one and one electron following the other. The action we're using is the same with a number of changes. Okay, so these are technical questions, and those people who are not interested in them, I'll come back. But here we have, actually, it's probably easier if I show you the formulas for the propagators. Okay, so this is what conventional quantum gravity would say. it would say that imagine a mass is propagating between these two space-time hypersurfaces. And in conventional quantum mechanics, it can emit a graviton and reabsorb it. And that's described by this formula here. So you have the ordinary, this is the action for the scalar field, but it could be an action for a particle. And it's propagating between two states. And then, of course, we have to functionally integrate over the gravitational metric. Now, what the CWL theory does is a little bit different. First of all, you actually sum over all possible interactions between all of the different paths, okay, which doesn't happen in conventional theory. But it's not, you might get the impression that all we're doing is somehow taking a large number of different particles or a large number of different fields here, and just simply, that the new theory is simply, if you like, a proliferation of particles or a proliferation of fields, and otherwise it's unmodified. But that's actually not true, because this is not a theory of multiple fields or multiple particles. This is for a single particle. So when you actually when you want to calculate the propagator, it looks at first as though you're just doing it for n different fields here. Notice, however, there's a crucial difference in the action of the gravitational field. It's multiplied by n, the number of paths. So that's already a big change in the rules. The second thing is that we actually then take a fractional power of this to get the correct propagator, and that restores everything to being for it to be one path. Sorry, every time I click on it. So technically, it starts off looking like what you're saying, but then it becomes quite different. So the experiments haven't been done yet. We don't even know what they're going to be done on, okay? So we, for example, worked out details for silicon dioxide, assuming a quartz system. And so then you get a 16-second oscillation time scale actually in the lowest spike here. And then if you put in so if one puts in, if one couples this particle to its environment, which of course always happens, then you can parameterize that by a Q factor. And so in this case, for the silicon dioxide particle, you have a path bunching time given here. Actually, one can work out the detailed dynamics, but I didn't want to go into that in this talk. And then one can, so then one can calculate the detailed time dependence. So if you tell me what system it's going to be, we have numbers. There are no adjustable parameters in the theory, so that can be done. It was, of course, a major effort to work it out for a real extended system of some shape. This in the form of a cube. If it was a different shape, this number would be different, and so on. But I just avoided putting all that detail in. Let me say that that the experimental group, particularly the LIGO group, they're interested in a null experiment. They don't want to do an experiment where they're messing around with Q factors and numbers and so forth. They want to do an experiment where quantum mechanics would give nothing, and this theory would give something. And then they can look at the numbers. And they have some very clever ideas about how to do that. And in my opinion, that's actually much better, because when you try and compare numbers involving these lengthy calculations, there's always going to be questions about some of the parameters. I mean, have you parameterized the dissipation properly, and so on and so on. So I think the idea of a null experiment is much better, and that's what they're working on.
But I mean, is it a question of in principle, the predictions could be made so precisely that if you make the measurement and you don't see the prediction, then it's ruled out?
Yes.
Or is there some tunable parameter buried in there that you could say,
no.
Well, no?
No, there are no tunable parameters here.
Okay, so in principle, there's a definitive prediction for an explicit setup.
Yes.
Yeah. Okay, that's good. That's clearer than I thought I was getting from the.
Right.
But it's just because I'm a skeptic, so I'm always skeptical. But that's good.
In discussions with the experimenters, they do have to worry about the most obscure problems. For example, the Vienna experiments, the biggest problem they have is the motion of the trams several blocks away, causing vibrations. So in fact, they do have a proposal to do this experiment in space. In fact, you may have come across it. It's called the macro proposal. On the other hand, the problems of vibration are something that LIGO worked with for a very long time and more or less solved. So I suspect that it won't be necessary to go into space to deal with them. As far as stray gravitational fields are concerned, they're actually fairly easy to manage because you can easily model them. So if you like, the gravitational perturbation from a nearby tram is easy to understand and take care of in the experiments. What they don't like is the vibrations that it causes. Okay, so Douglas, you probably know that, of course, there's a lot of strife between these different fields. And so, this is Horacio Guri, who is a string theorist, telling you that the only credible theory is superstring theory. But if you talk to somebody like Avoy Ashtekar, who is the founder of loop quantum gravity, then he will say no. And he will argue that loop quantum gravity could be tested cosmologically. In fact, Ashtekar is probably the only person in the loop quantum gravity community who's actually tried to think of ways in which it be tested. So, one can certainly hope for something like that. As to what loop, so loop quantum gravity doesn't really fit on the picture. It's asking for a substruct theory, and so it's outside of physics. My feeling is that if they can produce a testable prediction, and hopefully along your skeptical lines without adjustable parameters, then we should listen. But it doesn't fit into this framework, loop quantum gravity.
So I mean, they're not. I mean, to the extent that they're not compatible, so that if CWL, matches the experimental prediction, you would say we've proved that loop quantum gravity is wrong, or something, or is it just not? Do they not live in the same? If
you want my personal opinion, it's virtually impossible for people in loop quantum gravity to relate what they're doing even to conventional quantum field theory.
Sure.
So it's very, if loop quantum gravity was able to produce something that was confirmed by experiments in cosmology, and I have to say that the predictions that are out there now are extremely elastic, shall we say, then obviously we'd have to listen. But the question of whether or not you could relate CWL theory to loop quantum gravity, I haven't the faintest idea. Okay. I mean, it's impossible to relate loop quantum gravity even to conventional quantum field theory.
So it wouldn't change the current situation. But no. And string theory is completely compatible because it's a different thing entirely, or what?
String theory is not compatible. No, string theory is not compatible with CWL theory. Let me emphasize. Okay. String theory assumes that quantum mechanics is obeyed at all energies, all scales. So it is not compatible with CWL theory. What CWL theory is saying that this search here, which may take 400 years, is pointless.
Yeah.
Because we're looking in the wrong place.
So you could claim
actually the truth is much closer to home. That's why I say it's like, sorry.
So I mean, you could claim that a validation of CWL is ruling out string theory.
Insofar as all string theories assume that quantum mechanics is universally valid, then yes.
Yeah, no, it's just good. It's clear. It's much clearer when you just state it. It's good. It's good to hear.
Okay.
Because I don't understand how they fit or don't fit.
Yeah, the mass in that experiment is just way too small. So let me go back to, this picture that I showed here was, of course, not relevant to an extended mass, but it still gives you a guide. if you're talking about 10 to the 3 particles, then you're basically here. And so the energy scales are 10 to the minus 60 electron volts. That's simply not going to show up. Okay. Now,
I'm not sure if we're on the same slide that you're pointing at, Philip. Oh, there we go.
Yeah. Oh, I see. There's a time delay.
It was just slow. Yeah.
Okay. Now, I'm aware of these experiments. A number of such experiments are being planned. Actually, there's a meeting upcoming in a couple of weeks to celebrate the 90th birthday of Penrose, and I believe some of the people involved in that are presenting at that meeting. This is the question of how one is supposed to understand these experiments is something that causes a lot of debate, shall we say. For example, Bill Unruh here has very strong opinions about what those experiments can and can't do. Of course, I have the perspective of a condensed matter theorist on them. And my feeling is that as far as the physics of Bose condensation is concerned, that'll be very interesting. But as far as any tests of gravity, of whether or not gravity messes up quantum mechanics, or whether they look at quantum gravity, I don't think so. Yes, you're absolutely right. That's what makes those experiments interesting. It's what I was mentioning before. It's this. You see that the numbers that you're talking about are already in the range of the maximum that's been done before, and I see no reason why they can't push those Bose condensation superpositions to much higher numbers of particles, in which case that'll be very, very interesting. But not for quantum gravity.